Welcome back everyone to our video on finding area with double integrals. If we're thinking about finding the area of some region, here I've labeled my region R for region, and we're going to use a double integral to do it. So if I want to do this with a double integral, instead of thinking of long skinny rectangles that run vertically or horizontally through my region, what I'm going to think of is actually breaking it up in a grid-like structure. So I actually have rectangular boxes, pieces in here, giving us an approximation. You can see we're filling the space inside of our region here, but some of our boxes here are actually hanging outside of the region, right? So we're going to be maybe overestimating the area by just a little bit doing this. But if you think about one particular box, we're going to call the area of each little box, we're going to call that delta A for some amount of area, change in area, but really some amount of little bit of area here. So if we think about that, that's a rectangle, right? So it's going to have dimensions some amount of x and some amount of y, and the way we get the area for each of these little rectangular pieces is to multiply those together. In other words, our delta A is going to equal delta x times delta y, right? We'll get the width times the height here. That'll give us the area. Now what we'll do is we'll add up all of those, and then you'll think about what we did in single variable calculus, where we make the boxes smaller and smaller so that we don't have very much hanging over, and we get really, really close to this shape of the region R. Because our boxes are so small, we can pack them in so that they basically fit right along the border. In other words, as we allow our little bit of area to get smaller and smaller, we take more and more and more little rectangular pieces inside. As n approaches infinity, the number of little rectangular pieces inside approaches infinity, then what will happen is our delta x and our delta y will actually become some microscopic amount of x and microscopic amount of y. So this infinitesimal amount of width and height will multiply to give us an infinitesimal amount of area, a really small amount of stuff. This is going to be our unit of area in terms of using a double integral to find area in the plane. Now obviously we could have written our formula for the area instead of delta x times delta y. We could have written it the other way, delta y times delta x. So our microscopic unit of area may be written as dx dy, or it may be written as dy dx. And we'll make our decision for dx dy order or dy dx order based on the shape of the region that we are trying to find the area for. So this expression here is really telling us, okay, we're going to use a double integral over some region R. You'll notice the capital R under here, dA. Now remember that dA can mean a couple of different things. So this is just a short way of saying that it's up to you to look at the region R that you're trying to find the area of with this double integral and choose the order of integration, and then obviously the order that you choose will determine which bounds go where here, the x bounds and the y bounds. So remember, we can write this as the double integral over the region R dx dy, or we can write it as the double integral over the region R dy dx. What we'll be paying attention to specifically in this video is looking at the shape of our region R, and that will help us to determine if it might be easier to integrate dx dy order or dy dx order. Let's go through some examples now. First, we're going to start with a very easy region. We have a region that is all points where x is between 1 and 6 and y is between 2 and 5. And if you look at this for a while and think x from 1 to 6 and y from 2 to 5, what we're really finding is the area of a rectangular region. Now, a multiple integral is certainly overkill for finding the area of a rectangle. However, we're using this example to start out very basic and see how the method works. Okay, let me go ahead and label my axes here. So if my x values are from 1 to 6, then that means this is x equals 1 here, and this is x equals 6 way out here. That would make this y equal 2, and that would make this y equal to 5 here. And so what we'll do is we're going to actually set this up both ways and get practice doing it. So we're going to set up our double integral. I'm going to set this up dx dy first. Now once I've chosen an order, that tells me the method of how I can find my bounds. So I look at my outermost variable here, I have dy, so I'm going to choose some y value, and then I'm going to draw through my region in the x direction to get my bounds. So I pick a y value next to my region, let's say this y value here, and then I draw through in the x direction. And the order that I draw through will give me my bounds. So I enter the region at 1, so my lower bound is 1, and I leave the region at the value 6, so my upper bound for x is 6. And now our outermost bounds just need to be constants, and we simply need to go from the lowest y value to the highest y value. So the lowest y value here is 2, so we go ahead and say a lower bound of 2, and the uppermost y value is 5, so our upper bound is 5. If we go ahead and set up our other integral, so we'll set up our double integral now dy dx. So if I set up the order dy dx, that tells me, looking at the outermost idea, I want to fix an x value and draw through in the y direction to get my inside bounds here. So if I look at fixing some x value, let's say I just pick this one here, and then I draw through in the y direction. So I first enter the region right here at the value y equals 2, so that's my lower bound, and I leave the region, my biggest value, at y equals 5, so my upper bound is 5. Now, my bounds for my outer variable, I just simply look at what is the smallest value in the region for that variable. Well, the smallest value for x is at 1 here, so that will be my lower bound, and then the largest value for x in my region is 6, so we will go from 1 to 6. So you can see that with rectangles it's very easy, right? This looks like you might have expected just looking at the region itself. Let's go ahead and work these out and show that they work out to be the same thing. So if I just do the inside integral first, so that will leave me an integral still from 2 to 5. But if I just integrate dx, that will give me x, and I will evaluate it from 1 to 6, and then I will integrate that dy, right? So that will give me the integral from 2 to 5, and then I think I will get 6 minus 1 when I plug in my bounds for x. Obviously, this is going to be 5, right? So if we integrate 5 dy, then we'll end up with 5y, and we'll plug in our bounds 2 to 5. And without doing too much work here, 5 times 5 would be 25 here, minus 2 times 5 would be 10, and then 25 minus 10, we would get 15 for an answer here, square units. Let's look at this second one here. So here we would integrate dy from 2 to 5 first. So we'll leave our integral from 1 to 6. Integral dy is just y. And then we would plug in 2 and 5, and then we would integrate dx. Now that will give us the integral from 1 to 6 of, if I plug in 5 and 2, I'll get 5 minus 2 dx, and then of course this is going to be 3, so we'll integrate 3 dx, so that will give us 3x, and then we will plug in from 1 to 6. You'll find that when you plug in 6 you get 18, when you plug in 1 you get 3, and 18 minus 3 gives us the 15 as well. So either way that we do this, in either order, we will get an answer of 15 square units of area here. Let's look at another one of these that is not a rectangle. So here our region is the set of all points where x is between 0 and 4, and y is between 0 and the square root of x. So you can see we actually have a function here instead of a constant. If we graph this region, then our region will look like this. Y being between 0, which is the axis, and square root x, so this is the graph of y equals square root x here. And then we'll have from x equals 0 to x equals 4, and we'll be in between those two values there. Now if I set up my double integral, let's actually set this up in the opposite order last time. Let's do dy dx first. So if we do dy dx first, think about what that says. Look, outside here we have dx, so fix an x value and draw through in the y direction. So I'm going to fix some x value, let's say here, and I'm going to draw through in the y direction. So I first draw through this horizontal line, and that is y equals 0, right, on the axis. And then I leave the region through this curve, and that's y equals square root x. So here we'll get y equals square root x as our upper bound. Now, once we have our inner bounds, our outer bounds are just going to be constants. So if these are x bounds from x equals something to x equals something, then we just look at the smallest and largest x values. So here the smallest x value is 0, and here the largest x value is 4. So we'll be integrating from 0 to 4 dx. Let's go ahead and work this out. So if we do the inside integral here, just the integral dy, So we'll go ahead and keep our x equals 0 and our x equals 4. But if we integrate dy, that's just going to give us y. And now we should plug in our bounds of 0 and square root x. Now you'll notice that one of our bounds for integration is a variable, and that's okay because we have integration dx coming later, so having this variable x as a bound is all right. So if we plug this in, then we'll have the integral from 0 to 4 of square root x minus 0 dx. And obviously that's just going to give us square root x, right? So we'll have the integral from 0 to 4 of square root x dx. Okay, think of this as x to the 1/2 power. So when we integrate this, the power will go up by 1. We'll get x to the 3/2. Dividing by 3/2 would be the same as multiplying by 2/3. So we'll get 2/3 x to the 3/2, and then we'll evaluate from 0 to 4. So here we'll get 2/3, 4 to the 3/2, minus 0 to the 3/2. Well, I think 0 to the 3/2 is still 0, right? So let's just focus on this 4 to the 3/2. This says take the cube after you take the square root. So let's do this square root first. The square root of 4 would be 2, and then cube that 2, you'd get 8. So we would get 2/3 times 8. In other words, we would get 16 over 3 here for the area. Let's now go back and do our same integral here, but we're going to do it in the opposite order. So we're going to integrate dx dy now. So this tells me here that my inner bounds are x equal bounds, dx first, and then dy is last. So these are y equals bounds. Okay, so remember the method is to fix this value and draw through in this value. So we'll fix a y value and draw through in the x direction. So if I fix some y value and draw through in the x direction going positive, now I first enter my region on this curve, and this curve is y equals square root x, but we're integrating dx first, and I need an x equals statement. So an equivalent x equals statement would actually be x equals y squared for this curve. So I actually enter the region on x equals y squared, so we'll say x equals y squared, and I leave this region through the vertical line here, which is the line x equal to 4. So our first integral bounds are y squared to 4, and then if we look at our dy, our y bounds here, we just simply need to choose constant bounds. So the lowest y value will be here down on the axis, that's at y equals 0, and then our top y value is going to be up here at this highest point. Well, that is where y equals square root x, and if x is 4 here at this point, then y would be the square root of 4. In other words, this is a y value of 2 here. So we're actually integrating from 0 to 2 dy. Okay, let's go ahead and do our inside integral first. So if we integrate dx, let's leave our y integral alone. 0 to 2, integral dx will just be x. And we'll be plugging in from y squared to 4, and then evaluating dy. So plugging in our bounds, we'll get the integral from 0 to 2 of 4 minus, plugging in y squared, we just get 4 minus y squared, dy. So we have a nice easy integral to do from there. So integrating 4 dy will give us 4y, minus integrating y squared will give us 1/3 y cubed. And we'll be plugging in bounds 0 and 2. And if we plug in 2, then we'll get 4 times 2 is 8, minus 1/3 times 2 cubed. 2 cubed would be 8, so minus 1/3 times 8 would be minus 8/3. And then when we plug in 0 for each of these, we'll get 0 and 0, right? We'll get 8 minus 8/3, in other words, 24/3, minus 8/3, and you will see that this is also the same as our last one here, 16/3. Here I've got my region already drawn and my description up here. So my region is the set of all points where x is between 0 and 9 and y is between square root x and 3. Notice that square root x is my lower bound for y this time, and when you look at the region here, you can see that actually y equals square root x, that curve is actually the bottom of our region where before it was the top. Let's go ahead and set up our integral. Let's go ahead and do dy dx again this time first. And so that will give me y equals bounds on this inside integral, and it will give me x equals bounds on my outside integral. So looking here at dy dx, that means choose an x value, pick an x value, draw through in the y direction. So if I choose an x value, let's say here, and I draw through in the y direction, I first enter the region on this y equals square root x. So y equals square root x is my lower bound, and I come out the top of the region here at the horizontal line, that's y equals 3. So my bounds are square root x and 3 here. And now for my outer integral bounds, I will just need the constants that x is between. So here, the left side of my integral is at x equals 0, so x equals 0 is that bound. And over here, this very tip point here will be x equals something. If we could figure out what that is, I think maybe if y is 3 and y is the square root of x, so in other words, this is going to be 3 is equal to the square root of x. Can we figure out what x is? I think x is 9 here, right? So 9 will be our farthest right point for this. So we go ahead and do our inside integral first. If we integrate dy first, we'll leave our 0 and 9 bounds here. Integrating dy just gives us y. Always easy to start with that, isn't it? And then we'll evaluate from root x to 3. And then we'll integrate dx next. So we'll get the integral from 0 to 9 of 3 minus square root x dx. And now we'll integrate with respect to x. So here we'll get then 3x for the first term. Think of this like the power rule that we just did. So we'll get x to the 3/2. And we'll get a 2/3 out front of that. And then we'll evaluate from 0 to 9. So if we plug in 9 first, we'll get 3 times 9, that'll be 27, minus 9 to the 3/2. This is the square root, so square root of 9 would be 3, and then cubed would be 27. I get 27 times the 2/3. And then I have x here and here, so when I plug in 0, I'm just going to get 0. And you can go ahead and work out here, I think that 27 minus 27 divided by 3 would be 9, times 2 would be 18, so we'll get 27 minus 18, and that will give us an answer of 9 for this one. All right, if we go back and do our double integral in the order dx dy, then that means these will be x bounds in here, and these will be y bounds out here. So here with dx dy, we'll fix a y value and draw through in the x direction. So here I will choose this y value and draw through in the x direction. First I enter on the vertical line, that is x equals something, right? X equals 0. And then I come out on this curve. Now that's y equals x squared, but we need an x squared statement. So again, this is x equals y squared. So our integral is from 0 to y squared dx. And then the y bounds are just constants from lowest value to highest value. So the lowest value here is 0, y equals 0 is our lower bound. Our upper bound here for y is going to be 3. We'll go ahead and do our inside integral first. So we'll keep the 0 to 3. Integrating dx just gives you x. And you will plug in the bounds from 0 to y squared, and then integrate dy. If we plug that in, that's easy, right? Plugging in y squared for x, we would get y squared. Plugging in 0, we would get nothing. Y squared minus 0 is just going to give us y squared here. So we'll have the integral from 0 to 3 of y squared dy. That's just a basic power rule, right? You can do that. So we get 1/3 y cubed, and we'll be plugging in from 0 to 3. So here we'll take 1/3 y cubed, 1/3 times 3 cubed. 3 cubed is 27, 1/3 of 27 is 9, minus plugging in 0, 1/3 times 0 will give us 0, and then 9 minus 0 gives us 9, just like our dy dx. Okay, for these last three, we just want to give you an idea of how to set up a double integral and choose, is dx dy better or is dy dx better? There may be some times when one is far superior to another, and it's going to be based on the shape of your region and in which direction it is simpler. So some texts may call these type A and type B regions, or type 1 or type 2. Some sources will talk about something being x simple or y simple, which is the idea that we're going to go with explaining here. So if we first look at the order dx dy, that means fix a y value and draw through in the x direction. Will the rule for where you go in and out of the region always be the same based on that order? So if I choose a y value and draw through in the x direction, if I do it down here, I'm going in the vertical line and I'm coming out this line here that is y equals x plus 1. If I do it up here, the same thing happens. But if I go above this point here, let's say up here, then the rule is not the same, right? So it depends which y value I choose when I fix my y value and then draw through in the x direction. It's not always the same answer depending on where I fixed my y value. So this is not really simple in the x direction, okay? So dx dy is not so good. You can see up to this point here, we go in the vertical line and come out this line here, but then above this we go in this slant here and come out this slant. So you would really need two integrals to do this region. If we look at doing this region in the order dy dx, so we would fix an x value and draw through in the y direction and ask, is the rule for where I enter and exit the region always the same? And it turns out that it is. If I fix an x value, let's say there, and I draw through in the y direction, I'm entering the region on the line y equals x plus 1, and I'm exiting the region on the line y equals 1/2 x plus 3. No matter where I fix my x and draw through in the y direction under the region, so let's say over here, right, that is always going to be the same. I'm always entering the region through y equals x plus 1. I'm always leaving the region through y equals 1/2 x plus 3. So that tells me that this region is simple in the y direction, and that means that I want to integrate dy first. So I would choose the order dy dx for this integral. Okay, if we look at setting up a double integral dy dx for this region, so now look at what we have. When we fix an x and draw through in the y direction, I'm going through first, I'm entering the region at y equals x plus 1. I'm leaving the region through the top where y equals 1/2 x plus 3. And then I will need constant bounds for my x. So I look at the smallest x value, which is over here at x equals 0. And then if you can tell, our largest y value is here. So if we drop down to the x-axis, it's going to be right here. That's going to be at the intersection point of those two, right? So if I want to figure out where these intersect, I could set them equal to each other and say x plus 1 is equal to 1/2 x plus 3. And we can, of course, solve that, right? If I subtract half an x to the other side, I'll get half an x here. If I subtract 1 to the other side, I'll get 2 there. If I multiply by 2, I get that x equals 4. So that tells me that that's my upper bound for x. So this is the double integral that we would probably prefer for finding the area of this region here. Again, remember that this is simple in the y direction, so we choose the order dy dx. In other words, because it's y simple, we want to integrate dy first. Let's look at another region here. I have a line and then I have a parabola, and we want the region sort of bounded by those, and we want to choose, is it a dx dy or a dy dx preferred? So for this one, if I look at dx dy first, then I would choose a y value and draw through in the x direction. So I pick some y value. Do I always have the same thing happening? So here I go through the parabola first and I come out the line. Is that going to be true everywhere where I draw through in that direction? You can see that it is. Everywhere that we draw through in the increasing x direction, we're going to enter through the parabola, x equals y squared minus 1, and we're going to leave through the line y equals x minus 5. Okay, so we know that this is simple in the x direction. Is it simple in the y direction? Well, let's see. If we fix an x and draw through in the y direction, is that the same thing? So if I choose an x here, I draw through, I enter through the parabola and I leave through the parabola, which is weird because I don't want an upper and lower bound to be the same. I'd have to sort of cut this in half. So that's a problem already. But over here you can also tell, right? If I draw through in the y direction over here at this x value, I go through the line and then come out the parabola. So this is different than over here. So this is not y simple. This is going to be an x simple region. So we want to go back to this idea of choosing a y value and drawing through then in the x direction. So we will be integrating dx dy for this one. Okay, so if we set up our double integral dx dy, so I go in the parabola first. I need it to be in x equals because I'm integrating on the inside dx, and I already have it in x equals form, so I'll call that y squared minus 1. This upper bound would be the line, but this is in y equals form, so I need to change this, add 5 to both sides. This would give us x equals y plus 5. So our upper bound here will be x equals y plus 5. And then dy is our last thing, so we need our constants. We need our lowest y value and we need our highest y value. And if you can't tell because they're not really labeled here on the graph, then what we'll have to do is we'll have to set these equal to each other and figure this out, right? So since I already have both solved for x, let's go ahead and set y squared minus 1 equal to y plus 5. Okay, if I get everything on one side, that will tell me y squared minus y, subtract another 5, minus 6 is equal to 0. We could factor this. We'd get y minus 3 times y plus 2. All right, and setting those equal to 0, I think we can figure out that this lower y value here is going to end up being negative 2, and this upper y value here is going to be at positive 3 based on those solutions. So here we'll get y equals negative 2 as our lower bound. We'll get y equals positive 3 as our upper bound. So again, this is x simple, not y simple. So we choose the order dx dy. We choose x first because it's x simple. So here I have the axes as bounds, and then I also have this line y equals negative 2x plus 6, and I want to choose dx dy or dy dx based on is it x simple or y simple. Let's look at dx dy first. So if I choose a y and draw through in the x direction, is it simple to tell what's going on? So if I choose a y value and draw through in the x, it looks like I'm going through the vertical line and coming out the diagonal line, and that's always going to happen no matter which y I choose and draw through in the x. So I always get the same rule there. So that means that this one is x simple, and this order is going to work nicely for us. dy dx, that would mean choose an x value and draw through in the y direction. So if we do that, I choose an x and draw through in the y direction, you can see we're always, no matter where we are, going to enter the region through the horizontal line and come out the diagonal line, right? Even over here, we would enter through the horizontal line and we would exit through the diagonal line. So this is also y simple. So this is actually x simple and y simple. Either order is going to work just fine for us. So it doesn't really matter which way you do it. Find the area here. So now what I might do is, since I already have y in terms of x, y equals, just to save myself some time from having to resolve for this, maybe I go ahead and choose dy dx. So with dy dx, I'm going to fix an x value and draw through in the y direction. And so I enter the region at y equals 0, which is the axis, and I leave the region here through y equals negative 2x plus 6. And then what are my x bounds here and here? Well, this is certainly x equals 0 here. So we'll write x equals 0, and then we'll have to figure out x equals something here. Now this is on the axis, right? So figure out maybe this point is when y equals 0. So 0 equals negative 2x plus 6. I think after a second or two, you'll figure out that x is 3 here. So this will actually be a bound of x equals 3. But again, this is both x simple and y simple based on the shape of this region. So you can do this integral dx dy or integral dy dx, whichever you choose. Okay, hopefully this video helps you set up your double integrals. Thanks for watching, everybody. We'll see you in the next one.